Okay, now we're going to get into where physics and chemistry collide. Some of you will really like this. Some of you might not. I don't know. We'll see. Yes.
If that was an AP equation,
an AP equation, you would just write H2O goes to
H2 and O2.
H2 and O2.
Okay.
Yeah. That's it. So you balance it. It would be 2H2O goes to 2H2 plus O2. All right, number 13. Now these types of problems are basically, whoops, let's not show everybody's grades, are basically used for the production of certain things in industry. These are really applicable to those that work in industry and how you can figure out how much you're going to make if you run a certain current for a certain amount of time and all that. So one thing I need you to think about is an amp. Does anyone know what an amp is? Physics people.
It is the unit of current.
Okay. What are the units of current? Coulombs per second. So whenever you see an amp, I immediately want you to change it to a coulomb per second. And then what about, we also need to revisit the whole charge of a mole thing. That Faraday that we talked about yesterday is the connection between the physics world and the chemistry world. It brings us from a coulomb to a mole. And once we're in moles, I'm happy because it's chemistry. So what was that number?
96,500.
96,500 what per what?
Coulombs per mole.
Coulombs per every, so that's the charge of 1 mole of electrons, okay? Coulombs per moles of electrons. Knowing that, you can do these problems. These are super simple. But what I want you to do is look at the problem and write a half reaction kind of describing what's going on. We are producing, calculate the mass of copper metal produced during the passage of 2.50 amps of current through a solution of copper to sulfate. So we're making copper from copper 2. What would that half reaction look like?
Cu plus 2 plus 2e minus.
Cu plus 2 plus 2e minus makes Cu. That's crucial. It's crucial that you realize that's what's going on, which is not a big deal. Now notice it's we are actually electrolyzing copper 2 sulfate solution. So we're running both electrodes into the vat and we've got copper 2 sulfate and water going. So when we're starting these, we want to calculate the mass. We've got this number and we've got 50 minutes. I like to start with the simplest number. What do you think the simple number is with a simple unit? 50. So we're going to start it with the 50.0 minutes. Now looking at the fact that we need to get to amps and all that stuff, what do you think it's best to convert this to? Seconds. So for every 1 minute, I'm at 60 seconds. All right, now I'm in seconds. So now I can jump into physics world here, and I have 2.50 coulombs for every
1 second.
1 second. Coulombs per second. So now my seconds cancels and I'm in coulomb. Would you please get me out of physics hell and get me into chemistry world now? How do I do that?
96,000.
96,500 coulombs for every
Mole.
1 mole of electrons. Okay. Now I'm in a place where I can understand. Now we stoic, and this is why I wanted you to write this equation. Here's your mole of electrons. We ultimately want to get to grams of copper, right? So can I mole bridge over?
Yes.
So for every 2 moles of electrons I have 1 mole of copper. All right, get me to grams, chemistry people.
63.54.
63.54 grams of copper. 5.5? Okay.
5.4.
So to 3 sig figs, go ahead and give me the grammage, damage. Excuse me, home audience while I blow my nose. It's awesome.
2.47.
2.47 grams of copper is produced. So as a person in industry, say I was the copper producer on a mountain. I don't know why, I just think copper people should be on a mountain. I'd be like, hey, I need more. I need to make more. What can I do? Run it longer. I can increase my amps, or you can tweak all those. That's what this is for. It's pretty applicable to that. Now, looking at the next one, it says what volume of oxygen gas measured at STP is produced by the oxidation of water that occurs concurrently. Why is water being oxidized?
Cause sulfate isn't, it's a bit.
Sulfate's a bear, exactly. This is copper 2 sulfate. Sulfate's not going to be oxidized. Instead, water's going to be oxidized because water is more apt to be oxidized. Don't say because it's a bear. So, we're going to start. We're in the exact same situation. However, this is why you need to have the balanced half reaction. So let's go ahead and write water being oxidized. We make oxygen, and it is acidic. Okay. So now to balance that, we need a 2 there, a 4 there, and we need these numbers, okay, because we need that electron ratio in order to figure this out. It says, what volume of oxygen gas? So we're looking for liters of that. So we're going to be in the exact same cell, so we have the exact same setup. Our cell has the same time and amperage. So we're going to go with our 50 again. A lot of this is repeat. I'm going to convert that 50 minutes to seconds. I'm still at 2.50 coulombs per second. And I still have the good old Faraday to get me out of physics hell. But this time, I want to get, I'm not going all the way across, but what's my mole bridge?
4.
4 moles of electrons to 1 mole of O2. Uh-oh, I need liters. What do I do?
You use perfect.
Nice. For every 1 mole of O2, I have 22.4 liters. Before you go on, what if I were to say we were at 0.9 ATM and we were at 250 Kelvin?
Perfect.
What would I do though?
You take the moles.
Stop at moles and then plug into Pervner. Very nice. All right, give me 3 sig figs.
0.435 liters.
0.435 liters of O2. You all are rock stars. Super rock stars. I don't like number 15. I'm just saying. Let's just get rid of it. I don't like the way it asks. But I do want to do 16. This is kind of an extra credit problem. And advanced. It's awesome. That's not a sick cough. That's like me telling you to cough. I'm going to be very hands off on this. And this is all we're doing for the day. This is the end of the unit, by the way.
Woohoo.
It's sad, I know. We're going to be practicing because people are leaving for South Korea this week, so I wanted to get all the lectures in first. And we'll practice all week next week. And then it's spring break. All right. An aqueous solution of unknown salt of chromium is electrolyzed by a current of 3 amps for an hour. The process produces 1.94 grams of chromium metal at the cathode. What is the oxidation state of the chromium? So what are we doing? We are doing chromium plus
Something.
what? Yeah. Plus what electrons gives us chromium? So can anyone kind of tell me what we're looking for?
Trying to figure out how many moles of electrons.
Moles of electrons. It's like a ratio, right? Aren't we trying to find this ratio? Moles of electrons to what? To moles of chromium. So we need to find both those numbers. So how can I find, I can't believe y'all picked that up that fast. I'm impressed. Moles of electron, moles of chromium. So any ideas of how I can find moles of electrons?
Backwards.
Stoics.
Stoic. So we're going to start with 3 amps. This is the physics part of it, and this is the chemistry part of it, right? So for the moles of electrons, we got to get where electrons are important. That's the 3 amp. So 3, what's an amp again? Coulomb per second. Does it say how long we're running this? Oh, for an hour. So back up. We got to run it for an hour. We got to run it for an hour. So start with 3,600 seconds, right?
Yeah.
3,600 seconds. That's an hour for those of you listening. Equals 3,600 seconds. All right. 3,600 seconds. We're at 3.00 coulombs per second. How do I get to moles of electrons?
Faraday.
A Faraday. For every
96,500.
500 coulombs, I have 1 mole of electron, and that goes on top. So what is my moles of electrons?
0.112.
0.112. Okay. Now how do I get moles of chromium?
Using the grams.
We got grams of chromium. 1.94 grams For every 1 mole, I have, you all see it? I can't see it from here. 52.00. So what's my moles of?
10373.
0.0373. All right, and to get this, it's a ratio of moles of electrons to moles of chromium is our oxidation state. So what is that ratio? Should be pretty close to a whole number.
So 2.999.
So it's plus 3. The chromium is a plus 3. That's kind of sexy, yeah? Be able to find that like that? Didn't y'all like that? That was cool. All right, so let's give our home viewers the tour of, I'm going to get a ruler and point.
Should I move?
No, Dee, no, take it up there.
Okay.
All right, is it up there? Am I in it?
No, you're not in
Okay.
it.
That's the bear. The bears are what, y'all? Bears.
Group 1 and 2 metal
1
ions.
and 2 metal ions.
Polyatomic.
Here's polyatomic. She does not like the chihuahuas. The chihuahua won't attack her or him if water's present. If water's present, the chihuahua's going to attack the water. Okay? Wasn't there another one we looked at today?
We pointed out the
Okay, go to Vanna.
Where is that? There she is.
You're good, you're good.
Vanna White, EPA van. Okay? All right. Have a good day. Bye. Cut.
Brooks, you're so mean.
Well, I think it is.